Hey guys, what's up and welcome back to the Rocket Hub. My name is Philip and today we are finally bringing our series on the Raptor engine to an end and cover all the topics we haven't touched yet. This is the ultimate Raptor engine rundown.
3, 2, 1.
What you are currently watching is the third and final part of the ultimate Raptor engine rundown. Nearly everything in this video is based on the topics we have covered in parts 1 and 2, so it could be essential to watch the two other parts before you continue with this video. If you want to do so, they are linked in the description, in the end screen, and up there in the link function of YouTube. And of course, I have written down the timestamps again, so here they are. And I'm way too tired right now to speak out all disclaimers again, so let's just begin with the final part of our journey through the Raptor engine. The Raptor differs from other engines dramatically in nearly every dimension. It is designed to run on a new type of fuel, a better combustion cycle, and a more efficient ignition procedure. It possesses advanced gimbaling and throttling systems and is cooled by complex piping and double valves. But there are many more things the Raptor engine handles quite differently. Among those things are the combustion chamber fuel and oxidizer injectors. Even they have received some serious changes compared to most other engines, and especially the Merlin, SpaceX's engine that's currently powering the Falcon rockets. The Raptor now uses coaxial swirl injectors instead of the Merlin's spindle injectors. Injectors are the part of the engine that distributes the propellant and the oxidizer and mixes the two fluids for combustion. The typical pintle injector, like it is used on the Merlin engine, is coaxial, meaning it has two concentric tubes and a center stick that looks out a little bit like a lollipop. Fuel flows through the inner tube and oxidizer through the outer one. The oxidizer coming out of the outer tube flows out cylindrical, while the fuel in the inner tube hits the pintle in the center, letting it spray out in a conical pattern. When the fuel flow hits the oxygen flow on the outside, both fluid mix. But other than the Merlin, the Raptor injects gases, fuel, and oxygen into the combustion chamber and therefore requires a different type of injector. The so-called coaxial swirl injector differs from the pintle injector by having no pintle. Makes sense, right? The swirl injector has the same dual tube design as the pintle injector, with the fuel flowing in the center tube and the oxygen in the outer one. By creating a swirl in the inner tube, the fuel spins outwards in a spiral to create the same effect as the pintle injector does. But rocket engine injectors are really complex indeed, and that could maybe one day become a separate video, so we are not going too far here. And not just the injectors of the combustion chamber are different, but the combustion chamber itself is pretty advanced. To achieve maximum combustion efficiency, the pressure in the chamber is higher than in any engine before the Raptor. Burning methylax fuel at a pressure of just short of 330 atmospheres requires the combustion chamber to be way more resistant than usual. To maintain such a pressure, the walls of the chamber have to be extremely thick but stay as light as possible at the same time. The alloys used for the construction of the combustion chamber have to meet both requirements, which is really hard to achieve. But the combustion chamber is also much smaller compared to the rest of the engine than usual due to the Raptor being a gas burning engine, eliminating a lot of weight in the process. Another interesting way the Raptor differs from many engines is its manufacturing process. The Raptor is made almost entirely in-house by SpaceX itself and is designed to be mass-produced in short time intervals. At the same time, the engine production cost is lowered through the huge number of produced engines and the simplified design, yet still being one of the most complex engines ever developed. To achieve those goals, the Raptor is made out of metal alloys specifically developed for the engine, like the SX500 Inconel superalloy used for the Raptor's nozzle. Those alloys have the advantage of being specifically adapted to the area in the engines they are used at, and SpaceX knows every property of the material since they developed it themselves. Additionally to that, the Raptor is among the first engines to be at least partially 3D printed. About 40% of the early development engine's mass was 3D printed material. Although we have almost no information about the manufacturing methods used for the Raptor production today, we can still assume that main injectors and parts of the preburners and turbopumps to be 3D printed on a current iteration of the Raptor, just like in the earlier times. As you may have noticed over the course of the videos, the Raptor isn't just a single engine, and Raptor isn't equal to Raptor. There are multiple evolutionary stages of the engine, which are very different from each other. In fact, the first Raptor to be tested is so different from the engine we see right now that it could be another type of rocket engine as well. The Raptor has become a lot smaller, simpler, and more compact over time, and its performance got improved by a lot. But not only time has shaped the engine's appearance, there are a few different variations on the Raptor destined for specific tasks, and those variants of one and the same engine are not only designed differently, some of them have many parts the others don't. First of all, there is the base variant, or how it's often referred to, the sea-level variant. These are the Raptors we are pretty familiar with. They are being tested now for well over 4 years and have powered every Starship flight so far. The sea-level variant is specialized in operating in the lower parts of the atmosphere and possesses the ability to gimbal and has a huge throttle range as well. Due to its designated field of usage, the sea-level variant finds a compromise between high thrust, low weight, and high efficiency. With an enormous thrust-to-weight ratio and a specific impulse of over 300 seconds, it fulfills these requirements perfectly. The sea-level variant makes up the center cluster and the inner ring of the engines on the Super Heavy booster and the 3 center engines on Starship. They are mostly used for the vehicle's ascent and especially the landing burn. But in space, the sea-level variant has a massive problem. A rocket engine has something called the expansion ratio. That term tells us how big the difference in diameter is between the engine's throat and the outer edge of the engine's nozzle. And the expansion ratio is pretty important for thrust and specific impulse. Rockets get propelled by mass flowing in the opposite direction. In the atmosphere of Earth, the exhaust plume stays contained by the ambient pressure of the air around it. But in the higher layers of the atmosphere, the ambient pressure is so low that the exhaust plume starts to expand sidewards and grows dramatically in diameter. And due to some exhaust being sucked away to the side of the plume, the generated thrust decreases along with the engine's efficiency. Nozzle expansion defines the pressure at which the engine exhaust leaves the engine. The larger the nozzle, the smaller the pressure of the exhaust gets. If the pressure at the nozzle's exit is higher than the ambient pressure, the exhaust spreads outwards, the nozzle is now considered to be underexpanded. And underexpanded nozzles work very inefficient because the spreading plume loses a lot of potential energy. The larger the nozzle gets, the closer the pressure of the exhaust gets to the ambient pressure, and therefore the engine becomes more efficient. But making a nozzle too large makes it overexpanded, meaning the ambient pressure is way higher than the pressure of the exhaust, pressing it inwards. It has no big influence on the efficiency of the engine, but on the thrust output, and poses a huge risk to the engine due to something called flow separation being enabled to occur. In other words, the expansion ratio of just 40:1 on a sea level engine is far too less to operate efficiently in space. The solution for that is another variant of the Raptor engine, the Raptor vacuum, or short RVAC. The expansion ratio of the RVAC is something around 80:1 or even above, meaning it is almost ideal for in-space propulsion. And that's what it's used for. The three airbags are Starship propelled through the vacuum of space. With a specific impulse of about 380 seconds, the airbag is among the most efficient engines ever developed, despite having a fairly bad thrust-to-weight ratio. But that doesn't matter, since the airbag isn't supposed to lift off from anywhere. Talking about liftoff, there's a third variant of the Raptor as well. Based on the sea-level engines that make up the inner cluster of the Super Heavy's thrust structure, the outer ring is made out of 20 special so-called Raptor Boost engines. The Boost variant is basically the sea-level variant that lacks the ability to gimbal. These engines are not supposed to do anything except generating high thrust numbers, so they don't have to. The Boost variant is optimized for high thrust and low weight at the same time and will only fire during the first few hundred seconds of the flight and never get relit after MECO. Raptor isn't just Raptor, it is either Sea Level Raptor, Raptor Vacuum, or Raptor Boost. Now that you know about all the different versions of the Raptor engine and all of its game-changing design ideas, we can finally estimate how it compares to other engines that have achieved remarkable milestones in the history of spaceflight. At least our initial goal was trying to check whether the Raptor is the best engine we are able to create. But answering that may be impossible, and we may have to step away from that due to issues with different definitions of the best engine. We've mainly been talking about the engineering challenges on a Raptor and how the engineers solved them. But we haven't looked at how all those advancements impact on the Raptor's performance. So let's just do exactly that. Over the course of the decades, there were hundreds of different rocket engines developed. To compare the Raptor to other engines, we first have to select the competition. We need some other engines that have something in common with the Raptor itself or are considered to be some of the best rocket engines ever made too. Since some of these engines are only operating on sea level or in the vacuum and not both, we have to split the Raptor stats into the stats of the sea level variant and the RVAC. The booster engine is left out since that's basically the sea level variant and its stats are identical to that of the sea level variant. And remember, these stats are for the Raptor 1 as of August 2021 and may become outdated in the very near future when Raptor 2 goes online. So, in which categories do we compare the Raptor to its contestants? To get a rough idea of a rocket engine's performance, we have to take a look at multiple different stats. The most obvious one may be thrust, and we of course have to consider the total thrust output, although that may be a bit unfair due to the sizes of the different engines. To solve that problem, we incorporate the thrust-to-weight ratio, which is independent from the engine's sheer size. Then we have the weirdly defined specific impulse, or short ISP, to get a sense of efficiency for our contestants. But that isn't all. We also need to consider some real-world performance stats in terms of usability and reliability records. Additionally, the price of the engine plays an important role too, especially for single-use engines. Finally, we just have to choose which engines we are going to compare the Raptor to. We have the Raptor engine, of course, given. The first contestant will be the other engine developed by SpaceX, the kerosene-powered Merlin used on the Falcon rockets. Then we have the Rocketdyne RS-25, also known as the Space Shuttle main engine, which is considered to be the most efficient engine ever and is also going to power the Space Launch System, which is somewhat comparable to Starship in terms of size. Then we have the only other methane-powered engine in existence, the BE-4 by Blue Origin, as well as the F-1 engine, the most powerful engine of all time that powered the first stage of the Saturn V to the moon. So let's start gathering the stats. In terms of overall thrust, the Raptor has a targeted value of about 2.3 meganewtons for a sea-level engine, which hasn't actually been reached yet, but we are just short of it. Although that number may be the ultimate thrust goal that won't be exceeded anymore, we never know how far SpaceX will push its engine in the future, just saying. That is a fairly high number considering the Raptor being relatively small. SpaceX's other engine, the RP-1 powered Merlin, achieves a thrust level of about 854 kilonewtons or 0.8 meganewtons at sea level, since it is just so much smaller than the Raptor. The first competitor not made by SpaceX is the RS-25 with a total thrust output of about 1.86 meganewtons. The thrust of the RS-25 isn't even that high, but it doesn't have to since it is supported by two massive SRBs at liftoff and only powers the vehicle by itself when already in space. That's the reason why the nozzle of the RS-25 is slightly overextended at sea level. The next engine is a direct competitor to the Raptor. The methane-powered BE-4 is the power source of Blue Origin's enormous New Glenn rocket with a thrust output of about 2.4 meganewtons. That is also the engine that is going to power ULA's next-generation Vulcan rocket along with some SRBs, although Tory hasn't received his engines yet. And the last engine, the F1, the engine that brought humans to the moon, is the absolute king in terms of thrust with a total output of more than 6.7 meganewtons, more than double of the Raptor. And yes, I'm aware of that. Elon will call me fool now because I have measured this in meganewtons, but I can live with that.
Yeah, only a fool would use newtons, in my opinion.
As I've said, the thrust output alone doesn't state the entire truth about the actual work provided by the engine, since the sizes of the compared engines vary by a lot, and small engines are just not able to achieve the thrust levels of the F1, a true giant of a rocket engine. I mean, look at that thing, it's enormous. The better way to get an idea of the performance of an engine is the thrust to weight ratio, or how much thrust an engine produces per unit of weight. The Raptor produces a fairly high thrust numbers, while only being a mid-sized engine and giving it a thrust to weight ratio of around 200 to 1. Despite using a fuel with higher energy density than the Raptor's methane, the Merlin achieves a thrust to weight ratio that is even worse than the Raptor with about 158 to 1. I said even worse here, but that's still one of the best engines in terms of thrust to weight ratio that we have. The hydrogen-powered RS-25 has a good amount of thrust, but it weighs a lot and therefore only reaches a thrust to weight ratio of 73 to 1. Blue Origins keeps the stats of the BE-4 relatively secret, so we don't know the thrust to weight ratio of this engine. Considering the fact it is larger than a Raptor and at the same time produces less thrust, it should be around 100 to 1 or slightly above. And at the last, there is the F1 engine with a thrust ratio of just 94 to 1, despite being the most powerful rocket engine ever created. All in all, the Raptor is actually the king here. Now we get into engine efficiency, which is measured in the weird unit of specific impulse, or ISP, which is given in seconds. If you need an explanation for this unit and the reason why efficiency has a unit in seconds, you can go back to the chapter on rocket fuels in part 1 in our series. So, which engine is the most efficient? Generally, there are two numbers for specific impulse, one at sea level and one in the vacuum of space, since vacuum-optimized engines generally operate way more efficient than their sea level counterparts. The Raptor has a specific impulse of 330 seconds at sea level and the RVAC even reaches an ISP of up to 380 seconds, which is pretty impressive value as you will see soon. That has to do with the Raptor's fuel being methane, but it's mainly a result of the full flow stage combustion cycle's extremely efficient combustion. The other engine by SpaceX, the Merlin, has a specific impulse of 282 seconds at sea level and 311 in a vacuum. The RS-25 on the other side may be the most efficient engine ever, with an ISP of over 366 seconds at sea level and a whopping 452 seconds in a vacuum of space, beating even the Raptor by far. The F1 actually has a pretty high ISP for an RP1 engine, with 263 seconds at sea level and 304 seconds in space. The stats of the B4 are again unknown so far. But apart from those basic stats, there may be some other stats that are not so easy to define just on paper, but are rather based on real-life performance. One of them is engine reusability, something you need to consider when trying to push the cost of going to space down. Since Starship is developed with the goal of being fully reusable, the Raptor engine has to be capable of doing many flights. And when I say many, I mean a lot. In fact, the Raptor is designed for being reused as much as somehow possible, and SpaceX hopes to get its reusability up to 1,000 flights in the future. That would easily be a new world record. SpaceX's currently used engine, the Merlin, is capable of flying 10 times, although it may be able to go even further, but we will find out soon since it is already in operation and the first Falcon 9 boosters have reached their 10th flight. The RS-25 has a recorded history of being reused as well. Its record on 19 flights as the main engine of the space shuttle, but it won't be reused anymore on SS, so that record will always stay like this. Reusability is one of the only stats we have of the BE-4, which has a design goal of 25 flights. And the only not reusable engine in our comparison is the F1 back from the days when reusability wasn't really a thing. But just as important as reusability is reliability. The percentage of successful engine firings compared to the number of total ignitions. To fly humans to space, an engine has to be very reliable, but the Raptor has a pretty bad value here. We don't know the exact number of this engine, but it's likely going to be less than 90% when considering tests, and then maybe around 75 or a bit above percent during flight operations. But that's a side effect of still being in a prototyping state of development and will likely change in the future. The Merlin, on the other hand, has a reliability record of almost 100%. On more than 100 flights of the Falcon 9 and Heavy, the Merlin only malfunctioned a single time on ascent and just a few times on descent and landing. The RS-25 also has a record of nearly 100%. It just failed twice during the shuttle era, manifesting its reliability on a bit more than 99.5%. Since the B4 hasn't flown yet and probably won't fly in the near future, we don't have a reliability record available here. And the F1 just never failed. And the last factor is crucial for private spaceflight companies like SpaceX. We have been talking about production operation cost a lot on this channel. The less money an engine costs to produce and operate, the better it is suited to bring the cost of spaceflight down. The cost of producing one Raptor lays at an estimated $2 million, which is pretty low for such a complex engine. The Merlin is even cheaper at less than $1 million per engine in production, making it the cheapest engine on our list by far. The good old RS-25 is on opposite of the scale with a higher price of more than $50 million. NASA even paid Aerojet Rocketdyne a whopping $150 million per engine for the Artemis program. That's exactly the price of a Falcon Heavy, just for comparison. The BE-4 by Blue Origin is said to cost around $8 million per engine, placing it somewhere in the middle. And the last contender, the F1, would have cost around 30 million in today's dollars, since the prices we have of that engine are heavily influenced by inflation and other monetary things, because the dollar back in the 60s had a pretty different value from the dollar today. But the sheer production cost doesn't tell the entire truth. The cost per flight is what really tells us the economical viability of an engine. Since we don't have any clue on the cost of refurbishment operations, I haven't included those costs here. The values in this table are based on production cost divided by number of possible flights. And here the true potential of the Raptor becomes visible. It has a potential best case cost per flight of just $2,000, an astonishing value, far better than any other engine. The Merlin isn't quite as good as the Raptor, but still achieves a value of less than $90,000 per flight. And the RS-25 sits at an even higher cost per flight with $2.6 million, more than 1,000 times higher than the Raptor's value. The B4 is quite cheap as just $320,000 per flight, but still hundreds of times more than the Raptor. At last we have the F1, which is unfortunately not reusable and therefore receives a cost per flight value of $30 million. When compared to other engines, the Raptor shows its true potential. It generates high amounts of thrust respective to its size, has a very high specific impulse, and is highly reusable. The cost of operating the Raptor is by far lower than any other engine by a factor of hundreds to thousands of times. The only thing the Raptor doesn't beat its competitors in is reliability, but for such a complex engine still in development, the Raptor already works excellent. The real-world performance of the Raptor is what truly makes this engine so remarkable. It is more powerful, more efficient, cheaper, and better suited for use than any other engine currently in existence. The Raptor engine is truly revolutionary. By burning a new propellant in a combustion cycle that is basically the holy grail of rocketry, the Raptor achieves high efficiency, reusability, and thrust output at the same time. No other engine ever was able to combine those three properties as well as the Raptor does. Maybe because the Raptor is a first of its kind engine. All the engineering work that had to be done to create what we've been talking about for well over an hour now resulted in some of the most advanced technologies in terms of gimbaling, throttling, cooling, and ignition systems the aerospace industry has ever produced. But we also have to consider that the Raptor is still in development, and many mechanisms it uses may change a bit over time, but the basic stuff like the combustion cycle will stay the same, and we are slowly getting closer to completion of the Raptor's development. Due to the constant evolution of the engine, the Raptor still has the potential to boost its performance even further. Despite already having exceeded nearly every initial development goal, the Raptor isn't what it could ultimately become yet. Due to its enormous advancements in reusability and efficiency, the Raptor and similar engines will certainly play a huge role in the future of space exploration. SpaceX has demonstrated what many consider to be impossible, creating an almost perfect engine. Although the reliability record doesn't look too great yet, we have to consider that the Raptor is basically still in a prototype state. But if we give the development a few more years of time, we could in fact watch the Raptor becoming the best rocket engine ever created in many hindsights. It will be more efficient and able to fly more missions than every engine before, and will even beat the Merlin in time to thrust to weight ratio. The revolutionary full flow stage combustion cycle design and the usage of methane enabled the Raptor what no other engine was capable of before, making humanity multiplanetary. Bring humans on board Starship to the Moon, to Mars, and maybe even beyond, and at the same time change the way we see space and its beauty forever. The Raptor is possibly the best compromise of everything SpaceX needs to accomplish their goal of going fully reusable and onto Mars. By designing and engineering the heck out of the engine, the engineers at SpaceX have created something absolutely mind-blowing. An absolute masterclass of engineering, years ahead of its time. Finally, we are at the end of the Ultimate Raptor Engine Rundown series. If you have gotten to listen to me now, I'm really thankful for you all watching the piece of content I'm proud of the most till the very end. After more than 2 months of research, scripting, recording and cutting, I'm really happy to finally show you results. And because of all the effort, I'd really appreciate it if you hit the like button and subscribe to this channel to support my content. Please leave a comment what you think about the series for me to further improve my content for you. And until the next time, I'm out. Cheers.